Good evening, everyone. How is everyone doing this evening? I know, sorry that we have a class the night before your recess starts. I also apologize that this class is a bit chaotic, but me and my girlfriend has been moving since the weekend. So my home study is still in a bit of a mess. So sorry for the inconvenience that it took so long to set up the session, but luckily here we are. And thank you for sitting in this class. I know, especially the night before recess. I know you all probably want to go out and party and do a bit of stuff, but thank you for being here. So I'm sure you guys are probably looking very forward to and is very excited about recess. Study break, yeah, I understand what you guys are saying. I usually used it as a study break myself. Yeah, but luckily you don't have to attend classes during this break. I know it's a lot of work. So I'm not that much older than you guys. So I guess you guys are born, what, 2002, 2003, 2004. Okay. So I'm born in 92. So I'm about 10 to 12 years older than you guys. So not that much older than you guys. So I still remember my first year back in 2011 and my second year back in 2012. I was also looking forward to this recess as well, but unfortunately, you still have to do work during the recess, but at least you don't have to attend classes. So let's give another minute or two for more of our friends to join us. And while we are waiting for more of our friends to join us, the department has actually asked all lecturers to talk about the following topic with all our students. I want to ask you guys, are you coping with the workload? Are you coping with the pressure? And how are you handling it? Honestly, nope. Chemistry doesn't exist anymore. Nope. So, what are the modules that is the most troublesome for you guys? WTW, that is, I assume, a maths module. Chemistry. Okay, calculus. So I assume calculus, you are doing limits and differentiation. I know calculus one, especially in the first semester, is one hell of a subject. But the only thing I can tell you guys is it will become easier. So usually after this recess, you more or less have a hang on the workload and stress and pressure of university. But one thing to remember is your lecturers are there to help you. So if you're struggling with a concept, struggling with work, please approach your lecturers as soon as possible and talk to them about it. So they are there to help you. Mr. Marvel, you said, I think it's just teaching, not really the workload. So teaching, so it means a lot of modules or bad teachers. So if you have some bad teachers or lecturers, ask them if they can perhaps change their lecturing style. So they are there, so lecturers are there to help you. It's their job. So, oh, you did. So I don't know if you know about it. So if you have a problem with a lecturer or a certain module, the best practice is usually to go talk to the lecturer about it. So if the lecturer doesn't want to listen, then you can set up a petition in a class and you bring the petition to the lecturer. If that doesn't work, then you have two different routes you can take. So the one route is via the CSIR, and the CSIR will pursue the matter for you. The second one is you can do it via the academic staff route as well. So you vote the lecturer that doesn't work, then you go to the next person. So the next person, usually a lecturer, will report to a certain research group. Then you go to the head of that research group or the head of the cluster. And if that doesn't work, then you go to the head of the department. If that doesn't work, from the head of the department, you go to the dean. If the dean doesn't work, then you go to the registrar. If the registrar doesn't work, then you go to the deputy vice chancellor of teaching and learning. If that doesn't work, you go all the way to the vice chancellor. So yes, it's just a bunch of admin, but yes, there are options you can do. 17 modules of pain. Understand that in one piece of advice I have for you guys is don't burn out. So make a bit of time for yourself as well. So what I did in my undergrad is one night during the week I would take off. So and on that night I won't do work. So I will finish my classes for today. I would work until 5 o'clock the afternoon, and after that I won't work anymore. Just relax. Unless there's assignments or tests that I need to prepare for or work on, then I won't take off. And then the second thing I did was Fridays was my call it break day. So I would attend my classes on Fridays. But in between classes, I wouldn't do any work. And then after classes, I wouldn't do any work and just relax the Friday afternoon and Friday evening. Again, unless I have a test or assignment due on a Monday or next week that I need work. But you need to make time for yourself to relax. Otherwise, you guys are going to burn out. And then one thing to keep in mind is I try to keep an open door policy. So that means if you have a problem, you're more than welcome to pop by or bug me, and I will assist you to the best of my ability. Even if it's not regarding Psi 154, I will also always try to assist you in any means possible to try and help you guys. I know some of the other lecturers is not that way, but I'm always willing to help where I can. And I see, yeah, Mr. Melville, you say right now it's basically just self-study, basically leaving it to my class to sort it out because we all feel the same way. That is bad. Excuse me just 1 minute, guys. My phone's ringing. Sorry about that, guys. That was just an phone call I was waiting for the entire day. So yes, so I know some of your lecturers are horrible lecturers, and some stuff needs to be self-study. Unfortunately, but yes, you guys are allowed to complain about it. And usually, each semester, each lecturer will provide a teaching review that students can complete. Then, in that teaching review, you can also complain about it. So remember, from going forwards, if you guys need help with something, even if it's not Psi 154, I will always try and help. If I can't help, I will point you to a person that can help. So before we continue with our lecture, is there something you want me to recap? We did last week. Anybody still happy with the content of the work? Awesome. So I'm just going to go back. So I just went back a couple of slides of where we stopped last week. So we're going to start from the search for black holes again. So I just read the slides because that was she does but terribly. So I can just do a bit on my own. Okay, so let's start again from the search for black holes. So the first X-ray telescopes reached orbit in the 1970s, and that allowed astronomers to begin searching for evidence of black holes. They tried to find one or more objects that were obviously black holes. That very difficult search is a good illustration of how the unwritten rules of science help scientists understand nature. A black hole alone is totally invisible because nothing can escape from its event horizon. But if matter flows into a black hole, it will whirl through space through an accretion disk and become hot enough to emit X-rays before it reaches the event horizon. An isolated black hole in space will not have much matter flowing into it, but a black hole in a binary system might receive a steady flow of matter transferred from the companion star. This suggests you can search for black holes by looking closely at X-ray binaries. Some X-ray binaries, such as Hercules X1, contain a neutron star, and they will emit X-rays much as would a binary containing a black hole. You can tell the difference in two ways. If the compact object emits pulses, you notice a neutron star because a neutron star is a solid body within which powerful magnetic fields are generated, so meaning a pulsar. As the neutron star rotates, the magnetic field emits beams that sweep around the sky, producing pulses as they pass across Earth. A black hole inside its event horizon cannot emit regular pulses like those from a neutron star. Another clue depending on the mass of the object. If the mass of the compact object is greater than about 3 solar masses, it cannot be a neutron star, it must be a black hole. The first X-ray binary suspected of harboring a black hole was Cygnus X1, the first X-ray object discovered in the constellation Cygnus. It contains a supergiant star of spectral type B0 and a compact object orbiting each other with a period of 5.6 days. Astronomers suspected that X-rays were emitted by matter from the star flowing onto the compact object. That object is invisible, but Doppler shifts in the spectrum reveal the motion of the B0 star around the center of mass of the binary. From the geometry of the orbit, astronomers were able to calculate that the mass of the compact object had to be greater than 3.8 solar masses, well above the maximum for a neutron star. To confirm that black holes exist, astronomers needed a conclusive example, an object that couldn't be anything else. Cygnus X1 didn't quite pass that test when it was first discovered. Perhaps the B supergiant star was not a normal supergiant, and its portion of the system mass was incorrectly estimated, or perhaps the system contained a third star. Either possibility would distort the analysis. At the time, astronomers could not conclusively show that Cygnus X1 contained a black hole. It took years of work to understand Cygnus X1. Further observations and analysis showed that a B0 star has a mass of about 25 solar masses, and a compact object is about 10 times the mass of the Sun. Astronomers conclude that matter flows from B0 stars, a strong stellar wind, and much of that matter gets caught in a hot accretion disk about 5 times larger in diameter than the orbit of Earth's moon. The inner few hundred kilometers of the disk have a temperature of about 2 million Kelvin, so hot enough to radiate X-rays. So, how do you guys think the first black hole was detected? Let's have a little bit of a discussion about that. So in this conception, we can see the X-ray source, Cygnus X1, consists of a supergiant B star and a compact object orbiting each other. Gas from a supergiant stellar wind flows onto the hot accretion disk around a compact object, and X-rays astronomers detect come from the disk. So, if they were sure about the mass and surroundings, they could have concluded it. Yes, that is true. And but the same nova. So yes, you can calculate the mass. So if you have the mass, then yes, you can calculate it. And then that is an example of a black hole. So here we can see 6 black hole binaries that has been observed. So Cygnus X1 is a B1 type star. Its orbital period is 56 days. Then we have LMC, and here we can go on and on and on. So another way to confirm that black holes are real is to search for evidence of their distinguishing characteristics, so the event horizons. And that search has also been successful. So, remember being with the Event Horizon Telescope, we can see the X-ray accretion disk around the event horizon, and that was imaged by the Event Horizon Telescope. So here we can see a black hole X-ray nova. So the matter spiraling into the black hole vanishes with no detectable bursts of energy. And if it is a neutron star, then we can see matter spiraling into a neutron star hits the surface with a detectable burst of energy. So now we're going to start talking about compact objects with disks and jets. So matter flowing onto a neutron star or onto a black hole forms an accretion disk. And that can produce some surprising phenomena. Astronomers are just beginning to understand these peculiar effects. So what is meant with these surprising phenomena are these jets that are leaving the accretion disk. Do you guys have any idea what is happening? Light is bending, but not, that is true, but it's not exactly what I'm looking for. So transfer of matter, that has to do with transfer of matter. The matting is remediated by the magnetic field. Yes, that is true. So that is what I'm looking for. So shooting out light, no, a black hole can't shoot out light because nothing can escape the gravitational pull. Yes, Mr. Melville, that is correct. Hawking radiation. And yes, Mr. Wittendahl, exotic particle emission. That is what we're going to touch on now. So observations show that some compact objects are emitting jets of gas and radiation in opposite directions. These jets are similar to the bipolar outflows ejected by protostars, but much more powerful. The Cold War played a minor part in the story of neutron stars and black holes. In 1963, a nuclear test ban treaty was signed, and by 1968, the United States was able to put a series of satellites in orbit to watch for nuclear tests that were violations of the treaty. A nuclear detonation emits gamma rays, so the satellites were designed to watch for bursts of gamma rays coming from Earth. The experts were startled when the satellites detected about one gamma ray burst a day coming from space. When those data were finally declassified in 1973, astronomers realized that the bursts might be coming from neutron stars and black holes. These bursts are known as gamma ray bursts, or abbreviated GRBs. So here we can see, altered by gamma ray detectors on satellites, observers used one of the VLT, so that means the Very Large Telescope, 8.2-meter telescopes on a mountaintop of Chile, to image the location of the GRB only hours after the burst. The image at the top left shows the fading glow of the eruption. The image at top right, recorded 13 years before, reveals no trace of an object at that location of the GRB. The Hubble Space Telescope image at the bottom was recorded a year later and reveals a very faint distant galaxy at the location of the GRB. So gamma ray bursts are hard to study because they occur without warning and fade quickly. But starting in 1997, new satellites were put in orbit to detect gamma ray bursts. Their data show that there are two kinds of gamma ray bursts: short bursts that last 2 seconds, but longer bursts can go from tens of seconds up to several minutes. Specialized space observatories now can detect bursts, quickly determine their location in the sky, and immediately alert astronomers on the ground. When telescopes on Earth swiveled to image the locations of the bursts, they detected fading glows that resembled a supernova. Stellar interior models indicate that a star more massive than some upper limit of about 20 solar masses can exhaust its nuclear fuel and collapse directly into a black hole. Models showed that a collapsing star would conserve angular momentum and spin very rapidly, slowing the collapse of the equatorial parts of the star. The poles of the star would fall in quickly, and that would focus beams of intense radiation and eject gas that would blast out along the axis of rotation. Such an eruption has been called a hypernova. So this happens is, so the image on top, we can see the collapse of the core of a massive star begins along its axis of rotation. The rotation of the star slows the collapse of the equatorial regions. Within seconds, the remaining portions of the core fall in. Beams of gas and radiation strike surrounding gas and generate beams of gamma rays along the rotation axis. In the gamma ray bursts fades in seconds, and a hot accretion disk is left around the black hole. So when an extremely massive star collapses in a hypernova explosion, energy from the core is focused into beams of radiation and matter that point along the axis of rotation. This is thought to be the source of GRBs that last longer than 2 seconds. Short gamma ray bursts, on the other hand, don't seem to be associated with hypernovae. Some repeat, and these repeating bursts seem to be produced by neutron stars with magnetic fields 100 times stronger than that in a normal neutron star. Dubbed magnetars, these objects can produce bursts of gamma rays when shifts in the magnetic field drape the crust of the neutron stars, causing star quakes and releasing large amounts of energy. So in this image, we can see some neutron stars appear to have magnetic fields up to 1,000 times stronger than those normal neutron stars. These magnetars can produce bursts of gamma rays when shifts in the magnetic field rupture the rigid crust of the neutron star. Not all short gamma ray bursts are produced by magnetars. Some bursts have occurred in parts of distant galaxies where you would not expect to find the young massive stars that produce magnetars or hypernovae. And an afterglow doesn't resemble fading supernovae. These bursts might be produced by the merger of two neutron stars or a neutron star and a black hole that orbited each other, radiated orbital energy as gravitational radiation, and spiraled into each other. Such a collision would cause a violent explosion as the two objects merge to form a new larger black hole. The gamma ray burst and fading afterglow from neutron star plus black hole merger should be different from that produced by the merger of two neutron stars. Could a gamma ray burst occur near Earth? The nearest known binary pulsar is only about 3,000 light years from Earth. If a gamma ray burst occurred at that distance, the gamma rays would shower Earth with radiation equivalent to a 10,000 megaton nuclear blast, comparable to a full-scale nuclear war between superpowers. So the largest single bombs ever made released less than 100 megatons of energy. So if I'm not mistaken, I think the largest nuclear weapon created is currently, I think, the Satan II missile from Russia. I'm speaking on the correction, but I think the Satan II has the power to level the area the size of Texas. So the gamma rays could create enough nitric oxide in the atmosphere to produce intense acid rain and also would destroy the ozone layer, exposing life on Earth to deadly levels of solar ultraviolet radiation. Gamma ray bursts can occur relatively near the Earth as often as every few 100 million years, and could be one of the causes of the mass extinctions that show up in the fossil records. Isn't the Tsar bomb, and so I think the largest nuclear bomb that was ever tested was the Tsar bomb. But the Tsar bomb was, I think, a bigger one was created called the Satan. It's supposed to be more dangerous and more powerful than the Tsar. And I think the Russians now have the Satan II. But I may be mistaken. But I know the Tsar bomb is in the top 3 of the biggest nuclear weapons. So this might happen if a gamma ray burst near to Earth would cross Earth's path. So, do you recognize the HESS telescope in Namibia? Do you guys guess what it's used for? Yes, gamma ray bursts. So the HESS telescope was specifically built in Namibia because it is dry enough so you don't have water vapor in the atmosphere. There's a lot of South African universities that works on HESS, and HESS is developed to primarily look and observe gamma rays. So here is just a nice representation of what we are seeing when we observe the black hole through the Event Horizon Telescope. So here we can see the black hole shadow. Photon ring image of the disk's far side, the Doppler beaming, the accretion disk, and image of the disk's underside. And then on the death of Stephen Hawking, Professor Brian Greene posted this on Twitter, saying it is hard to express how utterly remarkable and astoundingly delightful it is that mathematical scribblings can predict something as bizarre as black holes. And then, looking to the skies, with sufficient diligence, we find them. And then this was posted by Neil deGrasse Tyson with the Event Horizon Telescope image. We've produced the first ever image of a supermassive black hole 55 million light years away. Response, ooh. And then scientists, we've concluded that humans are catastrophically warming Earth. Response, that conflicts with what I want to be true, so it must be false. Then Bill Nye, the science guy. How can we see a star that gives off no light of its own? Take a look. And that, ladies and gentlemen, was the lecture on neutron stars and black holes. Do you guys have any questions? So yes, Mr. Benedict, I agree. Brian Greene is one hell of a physicist. Why is everyone so quiet this evening? So before continuing with the next lecture set of lecture slides, I also want to ask you guys, how are you? Let me ask just to restate the question. So how are your moon assignments going? So could you explain how the moonrise and moonset timetable works again? What is the probability of Earth getting hit by a gamma ray burst? So the probability of Earth getting hit by a gamma ray burst is very, very, very low. So excuse the pun, but it's really astronomical. But every couple of 100 million years that can happen. So let me show you how that works again for moonrise and set time. So we just opened up. Let me just share this tab. Chrome tab. So can everyone see this website? Okay, so I'm in Johannesburg, so this is what I'm using. So this is at my location, but it shouldn't differ too much anywhere where you are. If you're in the Gauteng region, it shouldn't differ too much. But here we can see we are at the 11th of April. So where my cursor is now, this is where the moon, so this little shaded part, is where the moon is below the horizon. And you cannot see the moon. So here, when it's above the horizontal axis, here we can see the moon is above the horizon and we can observe it. But take note, the moon is rising at just before 3 in the afternoon. But remember, that shifts about 15 minutes each day. So between 40 and 50 minutes each day, because the moon travels roughly 13 degrees per day. So going to tomorrow, the moon will rise at 3:33. Going to Wednesday, the moon will rise at 4:08. So let's say, for interest's sake, you start your observations this evening, just as an example. So here we will see the moon's maximum will be at around about 8:30. But remember, the moonrise is later every day. So I would actually, for example, choose that you do the observations each night. So I'm thumb sucking this. So let's say 10 to 12. So 10 to 12, the moon is 30 degrees above the horizon. So let's go now to tomorrow evening. So we go to 10 to 12. We can see the moon is a little bit higher. Now we go to the 13th, 10 to 12. Moon is a little bit higher. So 10 to 12, the day afterwards, moon is a little bit higher. But we started on the 11th, so 10 days. Let's go to the 21st. So on the 21st, we can actually see the moon is now rising just before 10. So now if we go to just before 12, we will see the moon will be just below 30 degrees on the horizon. So that is a good time to select. So depending on where you are, when you want to do your observations and what dates you want to do the observations, please make sure you pick the time accordingly. So for example, don't make this mistake. Let's go to the 11th. You see, okay, maximum is at 8:15. But now let's go to the 10 days later. The moon is rising only at 10 to 10. So that means if we go to 8:15, the moon is still below the horizon and you are screwing up your observations. So please make sure you understand what's going on and plan accordingly. Does that help the explanation? Okay, I will post the link in the chat. Yes, so exactly. So above the horizon is when we start to see the moon. Yes. So should the first questions of the assignment be included in the body of the article, or should we start with the questions, then the article starting on the next page? So the question should be answered in the article. So for example, you can incorporate it into the article, or you can have a subsection in the article saying, heading saying, for example, questions, and you just answer the questions in that under that heading. So I think, so for the physical length of your article, I think in the guide I said a maximum something like 3 or 4 pages. But if you go or use more pages, I won't penalize you for that. So if you wanted to start today, for example, should we start at about 11 or so? I would say a little, if you want to start today, I would personally start a little bit later because you might run into problems at day 9 or 10 of the observation. So I would aim for about 12 o'clock or even 12:15, 12:30 if possible, but around about 12 o'clock should be fine. So what is recommended to answer the question? So there's nothing recommended. So what I can actually show you guys, so let me show you the marking rubric again. I will upload that as well. Let me just quickly find it. Let me upload a marking guide quickly to Blackboard. After class, I will upload it immediately. So here is how I will mark your assignment. So remember, the assignment has the same weighting as a semester test. So that is why you guys don't have 2 semester tests, but only a semester test and assignment. So the assignment counts a lot. The assignment counts 100 marks. So here, as you'll see, your questions. So to get between 0 and 3.4 out of 10 is little or no insight into the answering of the questions. To get between 7.5 and 10 marks out of 10, the questions were fully understood and answered in a well-constructed manner with full insight. And that is what I'm going to look for. Then, if you do your observations well, so if I can see observations, that's an easy 10 marks. Then I'm going to look at your logic and background information for the article. Then the calculation of the diameter of the moon, that's also easy marks. Then what research have you done? Then I'm going to look that you actually write a good conclusion. Then referencing. You can use any reference style that suits you, that you like best. I like to use the IEEE referencing style, but you guys are more than welcome to use the style that you prefer. So if you just add your references into your references properly, that's easy 10 marks. So formatting and layout. If your formatting and layout is correct, that's another easy 10 marks. Then from last year, please make sure your article goes through editing. So have at least a friend to read through it again. So if you have a few spelling mistakes, grammar mistakes, then you will get full marks. Remember, and I'm also looking for, and that is the most difficult part, you write this assignment in the third person. So you don't say, I have done the observations. You say, observations has been done. You don't say, I have found the following. You say, the following has been found. You don't use I, we, my. You always refer to it as the third person. And then lastly, I'm going to look at the scientific content for your assignment. So question, so what if you're changing locations a lot during the 14th of April? Are there any other times we can start our observations? Can we start a couple of days later than the 14th? Yes, you are more than welcome to start your observations at any time you would like. As long as I can see a minimum of 10 observations, then I'm happy. So you can even do your observations early next month if you want. That is why I'm giving you the entire semester to do these observations. The only reason I selected these dates in your assignment guide is because it is easy and convenient times to do observations. But if you want to plan around, then you are more than welcome to. Does this answer a few of your questions about the assignment? It's a pleasure. Any other questions, guys? I know the 14th of this month is, I know, late at night, but yes, you guys are more than welcome to pick what you want to use. So I just pick these days because it's convenient for me, because I do observations all the time. Yes, I have 2 telescopes at home. So I have a 4-inch Celestron, and I also have an 11-inch Celestron. The 14-inch is amazing, but it's only the only problem with the 11-inch is it is quite tedious to set up. So especially when I'm on my own, it's quite difficult to set up, but you can still manage as one person setting up. It helps if you have a second person around that can help you setting it up. So if I just want to do casual stargazing, I use my 4-inch. Also, if I'm traveling and I take my telescope with, so for example, if I'm going to star parties or outreach programs, I usually take the 4-inch, but 4-inch is good enough to do planetary observation and some deeper sky stuff. But I sometimes take the 11-inch along as well. So just double checking. So by starting by 12 or 12:30 today, we can still complete our observations around the same time without having to start from scratch. Yes, that is true. Yes, so unfortunately, so if you want to Google it, I have the 11-inch Lestron HD. So yes, unfortunately, that is expensive. Optics are expensive, but it's totally worthwhile. So regarding the moon assignment, would a distance above the horizon be an arm length ruler measurement converted to the scale of our drawing? Yes, though that is why, yes, you can do it that way. So there are actually a few things you can do. So that's one way you can do it. You're more than welcome to use other methods as well, but probably the easiest method you can use is the small angle formula. But you're more than welcome to use that as well. There's other methods you can use as well. So equatorial mount, so the, no, it's old azimuth mount. So yes, so I'm very happy with that scope. If you guys have any other questions, or are you happy to begin with the next set of lecture slides? Excellent. So before we start, I will create a Google forms you can fill in just to get a clear indication of numbers. But if we get permission from the HOD, would you guys like a stargazing evening on campus? Awesome. So with COVID, that has become a problem, but I see we have now not in the start regulations, and since the Disaster Management Act has been lifted, so I will ask the HOD if we can do it. So just to get a clear indication, if we do a stargazing evening, would you guys prefer the stargazing evening to be on a Monday or Tuesday evening after class, or on a Friday evening, or perhaps on a Saturday evening? Okay, so I see majority on a Monday evening. Okay. So we'll ask the HOD and see what we can organize. And then the only thing is we need a spot on campus that is not too obscured by buildings and trees. So if we can get permission, we can use the roof of the physics department. But I know the university has issues for people having roof access, since a few people committed suicide over the years from the Humanity Building. So we can try. So is Hillcrest campus not too bad for observations? Alcide de Villiers could also possibly work. So I will contact the HOD and see if we can make a plan. And then also still need to get permission from the HOD. But if we get permission, would you guys also like to visit Hot Rail? Okay, so that unfortunately we need to schedule a day for it. So if you want to do it in the week, we need to do it in a time slot where you don't miss too much classes. Otherwise, it will have to be over a weekend. Yes, that is also true, Mr. Neville, but I will ask the HOD and then I will get back to you guys. So, for this new set of lecture slides, we are now going to look and discuss the Milky Way galaxy. So, our galaxy. So, now we have looked at star formation, star depths, star distances, how we measure stuff in space. So, we have our basic understanding. But now we are going to look at our own galaxy and other galaxies as well, and galaxy evolution. So, this part of astronomy is known as cosmology. So, cosmologists doesn't look at individual objects, but they look at galaxies. So, one of my colleagues actually made a joke, and he is calling cosmologists the gynecologists of the universe. Yeah, so that is my weird colleague with his jokes. So, for this lecture, we are going to look at the discovery of the galaxy, the structure of the galaxy, spiral arms and star formation, the nucleus of the galaxy, and the origin and history of the Milky Way galaxy. So, what can you guys tell me about our own galaxy? So yes, we have a black hole at the center. It is big. So not really creamy, but through your naked eye, it can look milky. It's a spiral galaxy. Yes, you guys are true. Yes, the closest galaxy to Earth, to our galaxy, is the Andromeda Galaxy. So comparing Earth to the rest of the Milky Way galaxy, we are insignificant and small. That is all true. The Milky Way is a bit closer to the center of the galaxy, so the Milky Way is the name for our galaxy. So this is what cosmologists do. Cosmologists look at the galaxy as a whole and look at different galaxies and look at the entire universe. So yes, our galaxy is 75,000 light years in diameter. So this is a best model we have of our universe. So we have the Big Bang. Then after the Big Bang, we have the cosmic dark ages, when first stars appear, black holes and accretion disk, the reionization, modern galaxies, and now where we are 13.8 billion years later. So this is called the standard model. So everything we know about the universe fits into the standard model. So question, what caused the Big Bang? We have no idea what caused the Big Bang, and that is what cosmologists is trying to figure out. So if we look at our own galaxy, this is where we are located, right in one of the edge spiral arms. So this is one of the best images we have of our own Milky Way galaxy. So if we take our telescopes and point it towards our galaxy, we have this. So this is made by the Fermi All-Sky Survey. So here we can see right in the middle of our galaxy, we have intense radio waves being emitted. So you're all probably familiar with this image as well. So this is our Meerkat telescope. Can you guys guess what all of these bright dots in the background is? Yes, you are correct, Mr. Benedict. So all of these dots are galaxies that has been seen by the Meerkat telescope. So here we can, for example, see a galaxy that's a bit closer, and you can see radio streams being emitted from the galaxy that we are going to discuss, and here as well. So the most in-depth picture to this far we have of our own Milky Way galaxy is the Meerkat All-Sky Survey. So here we can see the center of our own galaxy that has intense radio waves being emitted from it. So here we can see a supernova remnant. And then one thing is we're still trying to determine, we don't know what is causing these filaments of electromagnetic radiation, or other words, radio waves. So we are still trying to determine what is causing these filaments. But if you want to show someone a very cool picture, this is a picture of the center of our galaxy, the best picture taken of the center of our galaxy. And then over here, you can actually see in this image, you can show someone is a supernova remnant. Looks somewhat like a highway as seen through a rainy windshield. Yes, you can describe it that way. So for some reason I've missed something. What are you guys fighting about in the comments? So, sir, do you think the Big Bang did come from quantum fluctuations? That could be, that is logical, and that is one of the theories, but we currently don't have direct proof. So all in well, it seems the math makes sense, but we need to observe it for it to be true, and that is where the problem comes in. So there are a bit of theories, but yes, that is one of them. And you are correct. So it seems if quantum fluctuations is a good option. So I ask, what caused the Big Bang? Because the Big Bang created the universe, then what created that? So that is an entirely different can of worms we can open going to that discussion. So if you open that discussion, is you start getting philosophical, and then you start asking, what caused the Big Bang? Was it a higher power? Is it quantum fluctuations? And then it doesn't matter where we are or where this happened. This always ends up in a debate between creationists and atheists. So let's not open up that can of worms tonight. But if you guys want to have a discussion on that and a bit of debate on that, we can schedule that on a different time. So I made a theory where it comes from fluctuations. I kind of want your opinion on it sometime. You are more than welcome to ask me. So I was told to stop thinking too much. No, don't think to always think too much. Go on. That's what we're supposed to do. That's why we are scientists. We now try to figure out. So don't limit yourself by not thinking about stuff. Main question. So each telescope group project has been manufactured to survey certain celestial phenomena and bodies. HESS, gamma ray bursts, Meerkat galaxies, Artemis radio. So different telescopes has been designed for a certain purpose. So HESS has been designed specifically for gamma rays, but Meerkat is the same as HADROW, and it's designed to look at radio waves. The only difference between HADROW and Meerkat, for example, is the size of the telescope. So one is an array, one is a single standing antenna. So it all depends what the telescope is designed. Certain telescopes are designed to look at lower frequencies, certain telescopes are designed to look at higher frequencies. And same in the optical range. Some is designed to look at certain optical wavelengths, some is designed to look more at near infrared. So yes, but we put all these images and data together. So, question, I thank you, sir. I've already gone through enough existential crisis. That's fair. So, Lol, I made a few theories and proposed it to my previous physics teachers. I thought of the big crunch, but it turns out I wasn't the first one to think of it. So, if you have theories, you're more than welcome to discuss with me. We can set up a time for that. So, okay, makes career paths easy in astronomy. So I lose sleep thinking about things like this. I don't know if it counts. So that is why. So we need to think about this stuff. So if you ever want a different, if you ever want to set up a little group where you want to discuss more of these things, then you guys are more than welcome to contact me, and we can set up a small meeting where a few of us can come together. And if you want to discuss a few deeper things, you guys are more than welcome to. If you want to discuss theories with me, you guys are more than welcome to. So, you have traced the life stories of stars from their birth in clouds of gas, and thus to their deaths as white dwarfs, neutron stars, or black holes. Now you are ready to step back and view stars in vast communities called galaxies. This chapter focuses on our home galaxy, the Milky Way, and addresses 5 important questions. What is the evidence that we live in a galaxy? Secondly, what is the evidence that our Milky Way galaxy is a spiral galaxy? Thirdly, what are the spiral arms of the Milky Way and other spiral galaxies? What is the nucleus of the Milky Way galaxy? And lastly, how did the Milky Way galaxy form and evolve? So I want to go on campus, but we weren't there that day. So you have recess. So unfortunately, I don't have recess. If I want a holiday, I need to put in leave for it. So if you want to make a specific appointment, then we can do it. Otherwise, when recess is over, I will most likely be a little bit more on campus than I am now. So, a few things I want to show you guys. Do you know what this is? No, this is actually a high-powered laser. So I don't think I'm going to be in Pretoria this weekend. There's quite a lot of spare time on semester this week. So if you are not in Pretoria itself, you can always just send me an email, and if you want to, we can set up a meeting over Google Meet, Skype, Zoom, whatever medium, if that will help. So yes, this is a giant laser. We have 3 of them. Let me give you my email address. I'm going to type it in the chat, the study guide as well. So we have 3 of these lasers. One we developed ourselves. This one is provided by Roscosmos, the Russian Space Agency, and we have one provided by NASA as well. So here we can see the laser firing over our telescope. So I've touched on this a little bit before, but we use these lasers to calculate distance to satellites. So satellites still needs to be monitored and double check where they are in orbit. So usually for low Earth orbit satellites, we can use GPS satellites, but who checks the GPS satellites or satellites even higher? And even though you can get the location from low Earth orbit satellites from GPS, you need to track those satellites as well. And each time there's a satellite launch, we need to do periodic tracking missions to get a satellite in orbit that doesn't hit debris or anything. So what happens is, this is a 1.3 gigawatt pulsed laser. So your normal red laser pointer that you guys play with or had played with is around about 0.03 milliwatts. This is 1.3 gigawatts pulsed laser. We have 3 of them. So you literally, so all satellites have, we call it corner reflectors on. It's just a prism. So if you shine a light into that prism, it reflects the incoming light directly to where it comes from. So we literally shoot the satellites with these lasers, and the laser beam reflects back. So we know what the speed of the laser beam is. We record for the time for it to return, and we can calculate the orbit of, or the location of, a satellite accurately to within 3 millimeters. So if a satellite is drifted out of orbit, we just let a company, organization, government, or whoever owns the satellite know your satellite's drifted out of orbit. You need to fire up your thrusters to push it back into orbit where it needs to be. So what happens if you get hit by one? You can get some serious damage. So for safety precautions, we have a radar just off our site. We can't allow to have a radar on our site because that will cause havoc on instrumentation. But just outside of our site that doesn't cause interference, we have a radar. So if an aircraft comes in within 10 kilometers of our site, the laser automatically turns off. And if we also have cameras next to the laser openings. So if anything moves in front of the camera, the laser also turns off immediately. So this Roscosmos laser, we have an effective range of about 350,000 kilometers out of it. Our NASA laser also is about 350,000 kilometer range, and then our lunar laser ranger that we use to shoot the giant reflector plates on the moon, we get a range of about 450,000 kilometers out of it. So you won't be dead if it shoots you far away, but at close distance, this can really cause some bad injuries. You will learn in this chapter how evidence reveals that you are inside a great wheel of stars, a galaxy. The Milky Way galaxy is over 80,000 light years in diameter and contains more than 100 billion stars. It is your galaxy because you live in it, but you are also a product of it because the stars in the Milky Way galaxy made many of the atoms in your body. You begin this chapter by pondering the notion that the stars belong to you. But when you reach the end of this chapter, you may realize that you also belong to the stars. So the question keeps me up at night. When all has been said and done, could it be that the reason we, as humans, will only know so much about the universe and not everything is because we are the product of the universe itself? So yes, that is what we're going to touch in this chapter as well. So we can also learn we are part of the universe and we are part of our own galaxy. It's like the great Carl Sagan said, we are all made of star stuff. Mine is time. What is time? So that is also a rabbit hole you can go down to or down in. So it seems odd to say that astronomers discovered something that is all around us. But isn't it obvious that we live in a galaxy? You might ask, how do we know what our galaxy is like? Nobody has ever seen it from the outside. Finding the evidence to answer that question was one of the greatest adventures in astronomy. Since ancient times, humanity has been aware of a hazy band of light in the sky. So if you ever had a dark place and you look up, you will see a hazy band. That's why it's called the Milky Way. So in image A, we can see nearby stars look bright and people around the world group them into different constellations. Nevertheless, the vast majority of stars in our galaxy that are visible from Earth merge into a faintly luminous path that circles the sky, the Milky Way. The artwork shows the location of a portion of the Milky Way near a few bright winter constellations. So in figure 12.5 and the star charts in Appendix B to locate other galaxies in the Milky Way. So in image B is the Andromeda Galaxy, also known as Messier 31. It's a spiral galaxy about 2.5 million light years from Earth. Looks somewhat like our galaxy would appear if you could view it from the same distance. The two oval patches to the upper right and lower right of the main galaxy's central bulge are small satellite galaxies. So here we can see the Andromeda galaxies. Here's a small satellite galaxy and another small satellite galaxy orbiting the Andromeda galaxy. The Milky Way galaxy also has two satellite galaxies called the Large and Small Magellanic Cloud. So question, I ask this sometimes, is pain the reason for our existence or is our existence the reason for our pain? But I think the answer is obvious. Okay, so you guys are really getting philosophical tonight. The ancient Greeks named the band galaxies Kuklos, meaning milky circle. The Romans referred to it as Via Lactea, meaning Milky Road or the Milky Way. It was not until Galileo used his telescope in 1610 that anyone realized the Milky Way is made of huge numbers of stars. Almost every celestial object you can see with your unaided eyes is part of the Milky Way galaxy. The only exception viewable from Earth's northern hemisphere is the Andromeda Galaxy, also known as Messier 31, abbreviated as M31. You can see the Andromeda Galaxy from the southern hemisphere, but it will be very close to the horizon, which is barely visible as a faint patch of light in a constellation Andromeda. You learn later in this chapter that our galaxy is also a spiral galaxy and seen from a distance would look somewhat like the Andromeda Galaxy. So here we can see the Great Star System, or the Milky Way star system. Galileo's telescope revealed that a glowing Milky Way is made up of stars, and later astronomers realized that a sun must be located in a great wheel-shaped cloud of stars, which they called the star system. That star system appears from our location inside it as the band of the Milky Way circling the sky. Now we have this chap called Thomas Wright. And do you guys know what he has written? So in this document we have on the right, we have his document of laws of nature and universe and his mathematical principles of Thomas Wright. And in 1750, Thomas Wright, drawing on the technology of the time, referred to the wheel-shaped star system as the grindstone universe, by analogy with the thick disk of stone used in mills. Wright used the term universe because so far as was known at the time, the Milky Way star system was the entire universe. In the late 18th century, astronomers Sir William Herschel and Caroline Herschel, Sir William Herschel's sister, set out to map the three-dimensional distribution of stars in the Milky Way. They assumed that they could see to the outer boundaries of the Milky Way in all directions, and hypothesized that by counting a number of stars that were visible in different directions, they could find the relative distances to the edge of the star distribution. If they saw many stars in one direction, they reasoned that the edge of the Milky Way in that direction is far away. If the telescope revealed fewer stars in either direction, they concluded that the edge must be closer, calling their method star gauging. They counted stars in 683 different directions in the sky and outlined a model of the star system. So here we can see in image A, in 1785, William Herschel published this diagram showing the shape of the star system as could be viewed edge-on from outside. And then in image B, the sun is located near the center of this grindstone model universe. So seen edge-on, Herschel's model of the star system was very irregular disk. So in his system is if our sun is over here, so the solar system, this is the stars you could see. So the disk shape of the star system reminded astronomers of the thick millstone disks used to grind flour. Their data indicated that the stars were arranged in a disk shape with the sun near the center. In some directions, the Herschel saw very few stars, and these holes in the sky produced great irregularities along the edge of the diagram. The model proposed by the Herschels was widely accepted and studied by other astronomers. The Herschels were not able to measure the size of the star system, but later researchers attempted to do so. By the early 20th century, astronomers had concluded that a star system's disk is about 10 kiloparsecs in diameter and 2 kiloparsecs thick. So remember, kiloparsecs is 1,000 parsecs. The Herschels assumed that they could see to the edge of the star system, but that was not correct. They were actually seeing only as far into the Milky Way as the interstellar dust permitted. At the time the Herschels did their work, astronomers did not understand that the interstellar medium partially blocks the passage of light. Because the Herschels counted roughly similar numbers of stars in most directions around the Milky Way, they incorrectly concluded that the sun is near the center of the star system. Furthermore, the holes in the sky observed by the Herschels are not empty but are known to be especially dense interstellar clouds, completely blocking the view of stars behind them. Modern astronomers know that the Milky Way galaxy is much larger than was first thought, and that the Sun is not at its center. How the human race realized the truth about the location universe is a story that begins with a woman studying stars that pulsate and leads to a man observing distant star clusters. So now we're going to look at variable stars and distance estimations. It is a common misconception that the stars are eternal and unchanging, but astronomers have known for centuries that some stars change in brightness. Of course, novae and supernovae appear, grow brighter, and then fade, but many stars change periodically, growing brighter, then fainter, then brighter, then fainter, and so on. Some of these variable stars are eclipsing binaries, but some are stars that pulsate like beating hearts. The period of pulsation is the time it takes a star to complete a cycle from bright to faint to bright again. In 1912, Henrietta Leavitt was studying a star cloud in the southern sky known as the Small Magellanic Cloud. On a photographic plate, she found many variable stars, and she noticed that the brightest and longest periods. She didn't know distance to the cloud, so she couldn't calculate absolute magnitudes, remember in chapter 8. But because all of the variables she was observing are in the same star cloud and can be assumed to be at about the same distance, she concluded that there is a relationship between period and luminosity. The variable stars Leavitt saw, called Shepaids, are named after the first such star discovered, Delta Shepei. Many Shepei variables are known today. They have pulsation periods of 1 to 60 days and line a region of the HR diagram known as the instability strip. So the instability strip on the HR diagram contains combinations of stellar temperatures and luminosities corresponding to unstable pulsating internal structures. The more massive a star is, the more luminous it is, and the larger in diameter it becomes when it leaves the main sequence. Those larger stars pulsate with longer periods when they pass through the instability strip. Therefore, because both luminosity and period of pulsation depend on mass, there is a relationship between period and luminosity. So here we can see is the instability strip located on the HR diagram. Shepaids are clearly giant and supergiant stars. A related kind of variable, the RR Lyrae stars, are named after the variable star RR in the constellation Lyra. They have a pulsation period of about half the luminosity end of the instability strip. Type 1 Shepaids have chemical compositions similar to that of the Sun. Type 2 Shepaids and RR Lyrae stars are poor in elements heavier than helium. Stars in the instability strip are unstable and pulsate because a layer of partially ionized helium in the star's atmosphere can absorb and release energy like a spring. In very hot stars, the layer is too high to make the star unstable, and in very cool stars, the layer is too low. Stars in an instability strip have this layer in just the right place to make them pulsate as energy flows out of their interiors. As stars evolve across the HR diagram into the instability strip, they become unstable. They stop pulsating when they evolve out of the strip. Massive stars are very luminous, and they cross the instability strip higher in the HR diagram. Because the massive stars are larger, they pulsate slower, just as large bells vibrate slower and have deeper tones. Lower mass stars are less luminous. cross the instability strip below in the HR diagram, and being smaller, pulsate faster. This explains why the long period Shepaids are more luminous than the short period Shepaids. Leavitt first noticed what is known as the period luminosity relation in 1912. So here we can see in this figure the period luminosity diagram is a graph of the brightness of variable stars versus the periods of pulsation. You can plot brightness as luminosity, but because the diagram is used in distance calculations, it is more convenient with absolute magnitude on the vertical axis. Modern astronomers know that there are two types of Shepaids, something that astronomers in the earlier 20th century could not recognize in their limited data. So here we can see the type 1, the classical Shepaid. So here is the location of the delta Shepaid. Here's the type 2 Shepaids, and here is the RR Lyraeus Shepaids. Humanity's understanding of the nature of the Milky Way began to change radically around the year 1920, when an astronomer named Arlo Shapley discovered how big the star system really is. Besides being one of the turning points of modern astronomy, Shapley's studies illustrates one of the most common techniques in astronomy. If you want to understand some of the basic ways astronomers find out about the universe, and Shapley's part of the story is worth following in detail. So I don't know if you guys realized, but the telescope he used is a 60-inch reflecting telescope. So you learned in chapter 10, section 1, that star clusters come in two quite different types, open clusters and globular clusters. Shapley began his research on star system by noticing that although open star clusters are scattered all along the Milky Way, more than half of globular clusters lie in or near the constellation Sagittarius. The globular clusters seem to be distributed in a great cloud with a center located in the direction of Sagittarius. So here we can see an open cluster M52. So open clusters lie along the Milky Way all around the sky. Then we can see here globular clusters are scattered over the entire sky but are strongly concentrated towards Sagittarius. So here we can see the Sagittarius constellation, Scorpius, and all of these red dots are globular clusters. Shapley assumed that the orbital motion of these clusters are controlled by the gravitation of the entire star system. And for that reason, he concluded that the center of the star system could not be near the Sun, but must lie somewhere towards Sagittarius. To find a distance to the center of the star system, and thus the size of the star system as a whole, Shapley needed to find a distance to the star clusters. But that was difficult too. The clusters are much too far away to have measurable parallaxes. They do, however, contain variable stars. And those were the beacons Shapley needed to find the distances to the clusters. Shapley knew about Leavitt's work on Shepaid variable stars. Shapley and other astronomers realized that the Shepaids could be used to determine distances if their true luminosities could be discovered. But because Shepaids are giant and supergiant stars, they are relatively rare. None lies close enough to Earth to have a measurable parallax. But their proper motions, so apparent slow movements across the sky due to their motions through space, can be measured. The more distant the star is, the smaller its proper motion tends to be. So proper motions contains clues to distance. Shapley found 11 Shepaids with measured proper motions and used the statistical process to find their average distance and thus their average absolute magnitude. Then he could replace Leavitt's apparent magnitudes on the vertical axis of the period luminosity diagram with absolute magnitudes representing true luminosities. So here we can see this image again. So here we can now see it's just absolute magnitudes on the y-axis. All of the stars in the diagram were thus calibrated as standard light sources that astronomers could use to find distances. Calibrations like this one are important tools in science. So how do we know calibration? How do you take the temperature of a vat of molten steel? Astronomers often say that Shapley calibrated the shapades for the determination of distance, meaning that he did all the detailed background work to determine the luminosities of shapades. After that, he and other astronomers could use his calibrated period luminosity diagram to find the distances to other shapades without repeating the detailed calibration. Calibration is actually very common in science because it saves a lot of time and effort. For example, engineers in steel mills must monitor the temperature of molten steel, but they can't dip a thermometer. Instead, they use a handheld device that measures the color of molten steel. Recall from Chapter 6, Section 2, that the color of blackbody radiation is determined by the temperature of the body emitting it. So molten steel emits visible and infrared radiation that is nearly perfect blackbody radiation. So the manufacturer can calibrate the engineer's device, says, to convert the measured color to temperature displayed on digital readouts. The engineers don't have to repeat the calibration every time. They just point their instrument at a molten steel and read off the temperature. Astronomers have made the same kind of color temperature calibration for stars. As you read about any science, notice how calibrations are used to simplify common measurements. But notice too how important it is to get the calibration right. An error in calibration can throw off every measurement made with that calibration. So once Shapley had calibrated the period luminosity relation, he could use it to find the distance to any cluster in which he could identify those types of variable stars. By taking a series of photographic plates over a number of nights, Shapley was able to pick out the variable stars in a cluster, measure the average apparent magnitude, and find the periods of pulsation. Knowing that, he could read the absolute magnitude of the period luminosity diagram. With the apparent magnitude and the absolute magnitude, he could calculate the distance to the star cluster. Shapley later wrote that it was late at night when he finally plotted the directions and distances to the globular clusters on graph paper and found that, just as he supposed, they formed a great swarm whose center lay many thousands of light years in the direction of Sagittarius, confirming his suspicions that the center of the star system was not near the Sun but was far away in Sagittarius. So here in image A, we can see Shapley's study of globular clusters showed that they were not centered on the Sun at the origin of the graph, but rather from a great cloud centered far away in the direction of Sagittarius. The distance on this graph, given in thousands of parsecs, corresponding to Shapley's original calibration, that produced distances more than 2 times larger than the modern values. Then in image B, looking towards Sagittarius at visual wavelengths, you see nothing to suggest that this is the center of a galaxy. Interstellar dust and gas block your view. Only the distribution of globular clusters told Shapley that the center lies in this direction. He found the only other person in the building, a cleaning lady, and the two stood looking at his graph as he explained that they were the only 2 people on Earth who understood at Luminos that humanity lives, not near the center of the small star system, but in the suburbs of the vast wheel of stars. It is important to note that there were problems with Shapley's calibrations and distance determinations. Shapley was able to observe the globular clusters at great distances because they lie outside the plane of the galaxy and are not dimmed much by the interstellar medium. But the shaped stars he used for calibration mostly lie in the plane of the galaxy and were strongly affected by extinction. Also, Shapley did not know there are several types of variable stars, but the ones he used for distance estimates were different from the ones he used for the calibration. Consequently, his estimate for the size of the galaxy shown in figure 12.6 was bigger than the modern value. Nevertheless, he got the main point right, that we are thousands of light years from the center of the galaxy. Building on Shapley's work, Other astronomers began to suspect that some of the faint patches of light visible through telescopes were other star systems. Within a few years, they found evidence that the faint patches of light were indeed other galaxies, much like our own Milky Way galaxy. Today, the largest telescopes can detect an estimated 100 billion galaxies similar to our own. Our home galaxy is special only in that it's our home. Shapley's study of star clusters led to the discovery that we live in a galaxy and that the universe is filled with similar galaxies. Like Copernicus, Shapley moved us from the center to the outskirts. A careful analysis of the structure of the galaxy will tell you the details about our real location. Astronomers commonly give the diameter of the Milky Way galaxy as approximately 25 kiloparsecs or 80,000 light years, and place the Sun about 2/3 of the way from the center of the edge. So here we can see here is the Sun, here is the central bulge, and here is the disk. So if we look at it sideways, we can see here is the Sun, here is the center bulge, and this is the disk, and here we can see our globular clusters, and this is the halo of the galaxy. So sketches of a Milky Way galaxy viewed face on and on edge. So note the position of the Sun and the distribution of globular clusters in halo. While blue stars light up the spiral arms, only the inner halo is shown here. At this scale, the entire halo would be larger than a dinner plate. The disk of the galaxy is often referred to as the disk component. It contains most of the galaxy's stars and nearly all of its gas and dust. Because the disk is home to the giant molecular clouds within which stars form, nearly all star formation in a galaxy takes place in the disk. Most of the stars in the disk are middle to lower main sequence stars like the Sun. A few are red giants and white dwarfs, and fewer still are brilliant blue and OB stars. Those hot, massive stars are rare, but they are so luminous that they provide much of the light from the disk. Although astronomers can survey the locations and distances of stars, they cannot cite a single number of the thickness of the disk because it lacks sharp boundaries. Also, the thickness of the disk depends on the kind of object studied. Stars like the Sun, with ages of a few billion years, lie within about 500 parsecs above and below the central plane. In comparison, the younger stars, including the O and B stars, and the gas and dust from which stars form, are confined to the thin disk extending only about 50 parsecs above and below the plane. In proportion to its diameter of about 25 kiloparsecs, the disk of the galaxy is thinner than a thin pizza crust. So here we can see in these infrared images, the entire sky has been projected onto ovals with the center of the galaxy at their respective centers. The central plane of the Milky Way extends from left to right, and in image A, we can see the central bulge is prominent at near infrared wavelengths, but dust clouds block the view through the plane. Then in image B, we can see interstellar dust emits blackbody radiation and glows brightly at longer wavelengths, so that's radio wavelengths. So here we can see these large and small Magellanicid clouds as well. If you look up or down out of the galaxy's disk, you are looking away from the dust and gas, so you can see into the galaxy's halo, the spherical cloud of stars and star clusters that contain almost no gas and dust. Because the halo contains no dense gas clouds, it cannot make new stars. Halo stars are old, cool, lower main sequence stars, red giants and white dwarfs. It is difficult to judge the extent of the halo, but it could have as much as 10 times the diameter of the visible disk. Around the center of our galaxy lies the central bulge, a flattened cloud of billions of stars about 6 kiloparsecs in diameter. Like the halo, it contains little gas and dust. Astronomers often refer to the halo and the central bulge together as the spherical component of the galaxy. The central bulge is the most crowded part of the spherical component. The central bulge, visible above and below the plane of the galaxy and through gaps in obscuring dust, consists mostly of stars that are old and cool like the stars in the halo. So here is the recap again. So here we can see the disk, here we can see the central bulge, and here we can see the halo. So, ladies and gentlemen, I think let's call this for evening, and we will continue this lecture after recess. So I will be active for another minute or two if you have more questions. Otherwise, have a wonderful evening. Thank you for attending this class, especially the night before your recess starts. So enjoy the recess. Try to take a little bit of a break. Good luck in capturing up on work, but otherwise have a wonderful evening and I will see you after recess. I know it's supposed to be a break, but I know you guys are going to do work, but try to take small breaks between your work. It will help. Pleasure, guys. So if there's no further questions, I am also going to log off. So have a wonderful evening. Enjoy your recess, and I will see you after recess. Goodbye, everyone.